Hello everyone. For our first topic of second semester, we are going to look at circular motion. So we are still working with our concepts of velocity, acceleration, force, but this time instead of things traveling in a straight line, we're going to worry about things traveling in a circle. So our target today is to be able to describe centripetal motion in terms of velocity, acceleration, and force. And our two essential questions: why is an object moving in a circle at constant speed said to be accelerating, and what causes the centripetal acceleration? In what direction is the acceleration? So the first thing I want to do is look at this word centripetal. Centripetal is another way to say circular, and you may have heard of something called centrifugal force. Well, that's not a real thing. It's sort of an imaginary thing. The real thing we're going to talk about here is centripetal force and centripetal acceleration, all right? So that's another way to say circular. So here we go with our background. Let's connect this to what we already know. Velocity is defined as the speed of an object, right? And speed is the change in distance over the change in time. And the direction of the object. So remember that velocity is a vector quantity, right? It has both size and direction. And if we want to talk about acceleration, we know that acceleration is a change in velocity over time. Well, since velocity includes both speed and direction, you can have acceleration if you change the speed. But what we're going to do this time is we are going to look at acceleration as a change in direction. So our object is going to be traveling at the same speed all the time, but it's going to change direction, so it still has some acceleration. All right, so here's our first question. Why is an object that is moving in a circle with constant speed, all right, that's what we said, constant speed, said to be accelerating? All right, so here's what I want you to do. I want you to imagine that in this circle right here, you're looking down on it from the top, okay? There's a stable point in the center, and it's attached to a string, and the string has a golf ball on one end, or whatever kind of thing you want it to be attached to. And this thing is going to be moving around the circle like this, okay? So its velocity is around the circle. Now our speed is going to be constant, but what's happening to the direction that this thing is moving? So it's moving like this, but then it's also moving that way, and it's moving this way, and it's moving like this. You get the idea, right? As you go around the circle, its direction is constantly changing. And because the direction is changing, that means that this thing is accelerating. All right? So let's come back over here, and we're going to say, does this thing have velocity? Well, yes, it does, because the distance is changing and the time is changing, right? Now, because this is a circle, we know that the distance is going to be the same as the circumference of the circle, so 2 pi r. Does that bring you back to your geometry days, right? The circumference of a circle is 2 pi r. And the time is going to be really specific, and we're going to call the time capital T, okay? Now, T always stands for time, whether it's a capital or a lowercase. Capital T is very specific. Capital T means the period of revolution. What does that mean? That means the time to go around the circle once. All right, so if we're looking at the period of revolution, how long does it take my golf ball to go around once from there to there? And that's the time. All right, and we're going to call that capital T, this period of the revolution. So whoops, that's not what I meant to do. Let's try again. Capital T. All right. So our thing has velocity, yes, because it's moving through a distance over a period of time. Does our thing also have acceleration? That's a little trickier. Does it have acceleration? Yes, it does. Why does it have acceleration? Because the direction is changing. Whoops, that should be an I. There we go. Even though the speed is constant. All right. So my thing does have acceleration. Yes, it does, because the direction is changing even though the speed is constant, right? So if you remember back up here at the top, we said that acceleration is the change in velocity over time. Velocity is the speed and the direction. So because the direction is changing, that means the velocity is changing, and that means there's acceleration. Okay? So what's our big idea here? Our big idea, an object moving in a circle has, at constant speed is accelerating because the direction changes. All right, so my object has a constant speed, but it does have acceleration because the direction's changing. All right, now we have a formula up here, 2 pi r over t. This is going to tell us the centripetal velocity. How do we find centripetal acceleration? So centripetal acceleration is going to be v squared over r. Okay, so here are our two new formulas. There's actually going to be a third one in a minute. For the first part of second semester, we have the circular or centripetal velocity formula, and the C just means in a circle. And we have our centripetal acceleration formula. Again, the C just means it's moving in a circle. Okay? So let's do a problem so you can see how this works. So it tells me that I have a ball at the end of a 1.4 meter string. Let's highlight. I feel like highlighting. I have a ball at the end of a 1.4 meter string is swung in a horizontal circle. It makes one revolution every 1.09 seconds. So what does that tell us? That tells us that this distance right here, that's the string, is 1.4 meters. And so think back to your geometry, that's our radius, right? 1.4 meters. And then it tells us it takes 1.09 seconds to go all the way around. That's our period of revolution, 1.09 seconds. We can know it's still a time number because it's still measured in seconds. Okay? And that's all the problem gives us. So let's see. Then we have to find the centripetal velocity. All right. So we know that our centripetal velocity is 2 pi r over capital T. So I'm going to take 2. I'm just going to use 3.14 for pi. That'll be accurate enough for us. Times 1.4 meters. Ooh, where'd the 1.4 meters come from? Good for you. That's the radius. And then down here, I need capital T, the period of revolution. So that's going to be my 1.09 seconds. That's how long it takes this thing to go all the way around the circle one time. All right, so I'm going to put this in my calculator. I have to simplify the top first, so that's going to be 8.792 over 1.09. And then when I divide that out, I am going to get 8.06. I'm going to round that to 8.1. It's still meters per second, right? Because this is still a velocity number. So that's the speed that my thing is going, 8.1 meters per second. All right, so now what am I going to do? Now I need to find the acceleration. So we know that centripetal acceleration, right? The C just means centripetal or circular, is v squared over r. Well, I just found v in the first part, so that's going to be 8.1 squared. The radius, r, hasn't changed. That's still 1.4 meters. So I'm going to plug that into my calculator. I'm going to do 8.1 squared first. And that's going to give me 65.61 over 1.4. And when I divide that out, I get 63. This is still acceleration, so it's meters per second squared. All right. So I want you to pause for just a minute. I want you to look back over this. Do you know why it's got acceleration? Can you tell me where R is? What does capital T mean? Okay, I want you to look back over all of that and make sure you're okay with it. All right, question number 2. What causes centripetal acceleration? And in what direction is the acceleration? So, again, this is back to first semester here. We know that all acceleration, what causes acceleration? You know this. What causes acceleration? Unbalanced. Yep, that's right. Forces. All acceleration is caused by an unbalanced force, right? Some kind of outside force acting on my object. So that means that there has to be a force acting on this object that's moving in a circle. Newton's law tells us, remember Newton's second law, F equals ma. Or if we wanted to, we could rearrange it. We could say A equals F over m. Whoops, my bad. Let's try that again, F over m. So all we're going to do here is we're going to add some C's. So that's our circular force. Is now mass times our circular acceleration. Or if you write it this way, circular acceleration is circular force divided by the mass, okay? All acceleration is caused by some kind of force. So if we look at this a little more closely, the important thing we're going to remember here is the direction of this force, right? It's all about direction. The direction of the acceleration and the direction of the force. Okay, so does this thing have acceleration? Well, yes, we know it does, right? Because the direction is changing. So let's take a look a little more closely at our second picture here. So here we have a person. The person is holding onto a string. The string is attached to a golf ball. I don't know why it's always golf balls in this chapter. It just is. And the golf ball is moving around the circle like this. Okay? Now, if we were to let go of the string, the golf ball wouldn't continue to move around in the circle anymore, would it? The golf ball would head off in this direction. You've probably done this. When you were swinging something around and let go of it, right? It doesn't go in a circle anymore. It goes off straight. So what we know is that the string must be pulling the thing, right, so that it stays in the circle. So the pull, we know a force is a push or a pull, right? So that means that the force is toward the center of the circle. Well, if the force is toward the center of the circle, that means the acceleration is also toward the center of the circle, right? They always go together. The unbalanced force and the acceleration always go together. So if I back this up, I can say that my velocity is around the circle, but my acceleration, right, and my force are toward the center of the circle. All right, so our acceleration, yes, acceleration is toward the center of the circle. Is there a force? Yes. And I forgot to change colors. My bad. Here we go. Yes! And it's also toward the center of the circle. Okay? These are always going to be the same. Right? The force causes the acceleration, so the force and the acceleration have to be in the same direction. All right. So here's our big idea. Here's our big idea. Centripetal, remember that's a fancy word for circular, acceleration is caused by a pulling force toward the center of the circle. Okay, so let's go ahead and we're going to do another example problem here. So I have a child riding a merry-go-round. The child is 6.3 meters from the center. What does that mean? That means right here, this distance right here, this is 6.3 meters from the center of the circle. Her speed is 4.1 meters per second, and her mass is 25 kilograms. All right, so I have a velocity of 4.1 meters per second. I have a mass of 25 kilograms. What about this 6.3 meters from the center to the edge? Oh, good for you. That's the radius, 6.3 meters. Okay, it says calculate the acceleration experienced by the child. All right, well, we know, here we go. We know that the centripetal acceleration is v squared over r. We know v is 4.1. We know r is 6.3. I'm going to square that first. I'm going to get 16.81. I'm going to divide by my radius, 6.3. I'm going to get 2.7 meters per second squared. That's the acceleration. Now it says find the force. Okay? Well, I know that my centripetal force is mass times centripetal acceleration. So I have 25 kilograms times my 2.7 meters per second squared. And I'm going to get 68. And these are newtons, right? Because it's a force. All right. So I want you to pause again. I want you to come back up here. Can you answer question number 2? What causes centripetal acceleration? And what direction is the acceleration? So you should be able to talk to me about the direction of the velocity, but also the direction of the acceleration and the direction of the force. All right, your turn. There are 3 multiple choice questions I want you to answer, and if it helps, here's a picture of a person swinging something in a circle. So again, we're holding on to it here. The object's out here. It's going around the circle like this, okay? And then you have a problem down here to calculate based on this picture. Remember that in this swing ride at the fair, this is the radius, right, of that swing. Okay? All right, if you have any questions, make sure you write them down so we can talk about them next class. See you soon.